Thank you. Thank you. Okay, so as I said, I've been a coward. I'm a coward, and I decided not to talk about persistent homology when it was planned and to leave it afterwards, after you hear from more people, so I can posets, you know about them. Okay, so the last two lectures will be about persistent homology with the Emil flavor, of course. But, so I decided that this. So in the beginning, I thought there will be 2, 2, and 2, 6 classes without problem sessions. That's how I prepared my course. So this last part is a bit shorter, but it was supposed to show some different aspects. And this is somehow different in spirit from the rest. Okay, so it's about metric invariance. So why? I mean, okay, so you have these discrete curvatures, which can be simple to use, complicated to understand, and so on and so forth. And you might have some topological approaches like persistent homology. But in the end, you would like to use the simplest notion and try to see if it works. So the simplest, again, the simplest geometry you can presume or impose on your data, it's a metric structure. Okay? So that's the idea. It's go for the simplest possible approach you can imagine, metric one. And my idea is to try and do it in a spirit of pattern recognition and try to understand better about networks or cloud of points, textures, and so on and so forth. So there is another thing which I like very much in this. I was attracted by these ideas is that they allow you to look at many scales. So if you remember, there was this discussion, the last talk before me, that you theoretically you should or could compute persistent homology in all dimensions. But of course, practice makes this prohibitive. On the other hand, it might be that some structures look the same in dimension 2, but the fine distinction comes in dimension 3 or 4, whatever. And therefore, I like this, since I spent some time in electrical engineering, I like looking at many scales, if possible. I don't pretend this is a magic bullet or something. It's just an idea, okay? So I have something to try to convince you that it might be useful. It might be that idea is, so again, an idea might be very simple, yet implementation might be very costly. Okay, so my approach is, I'm trying to sell this kind of older papers of Grove and Mark Vorksen about curvature, triameter, and beyond. And there is yet another paper. This is one I used. And by the way, you see it's Alexandrov geometry. So it's so there are a few invariants which I think they are good to look at. It's very empirical. What I'm showing you now is not going at all in the depth of Grove's and Mark Vorksen work, but it's more the basic idea and how to try and use it in a practical setting. Okay, so the first definition is this of extent. So if you have a compact metric space, the Q extent is a maximal average distance between Q tuples of points. So you look at the maximal distance, you look at all the points, you take the distances between them, you take the maximum, and you divide it by the number of points in your configuration. I forgot to say that here I'm looking at up to n, yes? So if I have n points, I look at all the Q tuples from 1, 2, 3 till n, okay? It's something missing. I made a few corrections, but this I forgot to make. So you might compute it, so you might achieve it for some specific Q points. And these specific Q points, which realize the Q extent, is called a Q extender. Okay. So in the limit, so then you can take more and more Qs. Then it should be a Q here. Then as Q tends to infinity, you get the extent of your metric space. So if it's a finite metric space, like we work with, it's kind of easy. But if you have an infinite number, then of course, it might take some time to compute. Okay, so it turns out that, of course, when Q equals 2, this is just a diameter. So it's something that we know. And so when a Q is 2, we call it diameter. So it's very natural to call the other ones triameter, quadrameter, and so on and so forth. Okay, so in a sense, they are generalizations. Even if you don't want to look at more deeper geometry, these are generalization of the notion of diameter, yes? Oh, it should be Q here, either. By reflex, I wrote an N and I forgot to correct it.
What is the interest in defining the distance for this and not the distance between their like centroids?
There are approaches when you look at centroids, but for that you have to define them. This is, I mean, I'm not saying it's better. There is no better. You might say that a field is better than a group, but I like groups better. Yeah, okay. But this is more simple. I mean, you don't have to compute an extra point, so on and so forth. There is a problem with centroids. You might want to look, by the way, there is some work on this kind of generalized Menger curvature due to Jürgen, which I mentioned earlier, Jürgen Jost, and then using some notion of centroid, it might exist or it might not exist. Whereas these kind of guys always exist, which is a plus. Okay? It's not an elegant way to do things, just sound, I would say. Okay, so then you have this kind of sequence of inequalities. The extent 2 is greater than extent 3, and it tends to the extent of the space. And moreover, they can't explode. They are the extent of a space, it's between the diameter and half of the diameter. So it gives you, in a sense, the extent, it gives you a good approximation of size. Yes, it's just another version of diameter up to. Okay. So now a remark. Oops. It should have been a pause here. So this is an important thing. Extents are sensitive to asymmetries of the space. Why? Because if you have what does mean asymmetry? Asymmetry means that, so I have a configuration which is kind of dense, and then I have a point here. But once I have a point which is very far away, this distance, then this distance will be, the mean distance with other points will be very big. So it will change this mean very strongly, okay? So looking at asymmetries is a very important thing because if I may, okay, so I have some education, late education in imaging. So asymmetries are important because, for instance, good things are symmetric. If you look at a network, brain network, you know, how do you distinguish between some good mole or some good growth and a cancer one? What's the main difference between something which is benign and something which is malignant? Yes, it's very asymmetric, yes, it's chaotic. And therefore, if I want to use it, I'm glad to use measures which detect asymmetries, okay? Also, I would, okay. And then this is something that for me, it's very important. But that is something that Grove and Mark Vorksen said. They are can be viewed as global shape invariants. Again, they are global because I'm going over all the points in the space. And they encode shape because they talk about symmetry and / asymmetry. And therefore, they should be viewed. So what they say, they should be viewed as complements of local notions of local characterized means of characterizing a space, i.e. metric curvature. So curvature is a local notion. So this should be viewed as complements. So their results play a bit on this card. How should I compare them? How can I say something about given curvature and extent, let's say, can I say something about the space? And they can say a lot of things, which I won't go into them, but this should talk to you guys because you like all this topology stuff. They characterize not just the metric, but also the topology of the space. So you can say, oh, space which has such extent is a homology sphere, stuff like that. This is good. So you can detect spheres, for instance, or suspensions of spheres or stuff like that. So they are much deeper than they look. But that's what Grove and Mark Vorksen say, who are geometers. I mean, at least Grove. I forgot Mark Vorksen works in, is a polytechnic in Denmark, I think, sorry. I don't know. I mean, I apologize if he sees this recording, I do apologize. But I forgot. I'm too old. But what I'm trying to say is that for my viewpoint, they are really complementary. So when you want to use something, by now, this is something which you discuss also in less informal meetings and discussions, is that you can't hope to get everything so just one trick, be it curvature or be it persistent homology or be it wavelets or be it whatever. Usually, if things are a bit more complicated, data is more tricky than you might hope. Therefore, it's good to combine topology and geometry and analysis, and so on and so forth, probability and geometry, I don't know. So in my view, this should be used as tools in tandem with metric curvatures. Look at global invariance and local invariance as well. Okay, so this is a sphere and this is a sphere topologically, but locally they have different geometry. So if I can look at both local and global aspect, then perhaps I can characterize my space much better. Critics everywhere, yes. Okay, so I think that's my goal in using this invariance. They are simple. They are so simple that at least theoretically you don't have to be a very smart encoder to write. Mark Vorksen. The name is. Sorry? Ah, yes. These are black and white birds. These are these. They are very smart and very vindictive, by the way, and they do steal stuff. Anyhow, so that's why I'm trying to sell this invariance, okay? So in a sense, it would be a concluding, it should, in a sense, it should have been the last talk, but on the other hand, I felt it's more natural to sell them after all this talk about curvatures and not do persistent homology and go back. Also, I'm sure the last meeting, nobody will be here anymore, so it's better. Okay, so now these are related to some other notion, which is classical in geometry, which calls the excess of a triangle. So if you have a triangle, my triangles are always ABC. Well, in this case, it's not ABC, X, P, and Q, but the sides will be A, B, and C. So the excess as viewed from X would be C, A plus B minus C, yes? And we know this is always positive, yes? So of course, the smaller it is, so excess is something, so this triangle has a very small excess, yes? This one has very large excess and this one has almost no excess. It's almost flat. So excess is a measure of flatness. For those who know a bit of graphics, this is aspect ratio more or less. It's not quite, but it's very similar. So, okay, so this is the excess. And of course, it depends on the side. So if you have a very flat triangle, but these are stars at I don't know how many light years away, the excess will be very large, although the triangle is very flat, small parallax. Yes. Okay, so as I said, this is a classical notion, and I'll tell you where it appears. Okay, so the excess, so this is excess of one triangle, and then you go over all the triangles, and this is the excess of the space. Okay, you look at the maximum of the excesses for a triangle, and then you go over all the possible triangles of the space. Okay, so this is excess of the space. And there are global and local versions. There is some classical by now work of Otsu, a Japanese mathematician. So they are very good at this metric geometry and metric measure geometry kind of spaces geometry. And there you have a global version and you have a local version. I won't get too much into them because, again, I'm just trying to show you where I come from and not trying to make a course in Mark-Vorsen invariance. And what can we say? We know that excess is smaller than diameter, of course, for sure. Remember how it's defined, yes? And there is a connection between them, which I won't prove, which says that there is a connection between extent and excess. There appear very different notions. But in fact, if you have a small extent, you have small excess. Therefore, you can say something and say excess is a simple thing to measure. Once you find the excess and this is big, you know that something is wrong on the extent size. And this can be written in a quantitative form like that. Okay. And it turns the other way, it's not true. So you have something which satisfies this, but it doesn't satisfy the opposite inequality. And I had an extra line which says that, in fact, it's kind of depends on the dimension. If it's odd, it's one thing. If it's even the other thing, I don't remember the result. It's not important for us, anyhow. Okay, so what does it mean that you have local excess? It means small excess. It means that your geodesic, your shortest curve, is very close, yes, to P. It's clear that that's the meaning of it. So remember that what I draw here is a shortest line, the geodesic, yes? So if this is my point X, and this is very small in a neighborhood, it means that I have a geodesic close to my point. And this is important. It means that at least locally, I am very close to be able to really measure distances, so to say. Okay, so I'm saying that, I don't know, is this a clear statement that because this happens, it's clear that curvature and excess are closely related? Okay. So okay, so let me put it this way. Okay, so if you remember, so that's why I needed, perhaps this will help a bit. You remember that we discussed about Hante's curvature? So what was, when I have a triangle, So the Hantius curvature, first of all, you have this expression L minus D divided by D to the third, yes? But what is L? L is this distance, so this is L, this is A plus B. And the D is equals 3 in my, so L minus D for a triangle is nothing but A plus B minus C, I the excess. So in a sense, so Hantius curvature measures the extent of the triangle, but normalized, so you'll have the proper dimensionality, yes? That's what it does. So Hantius curvature is nothing by excess. So I should say that this is the metric curvatures, but there are classical results in proper Riemannian geometry which connect excess and Ricci curvature. Again, why? Because you just look at the deviation of your space from being flat, how fast geodesics diverge. But excess does precisely that. Okay, so this is one version of doing it. And now if I want to apply it to networks or to data, I don't need this. Okay, so this to the third instead of D is for normalization, so for scaling. But in a network, you don't, perhaps you want to look at the scale if it's a very big and self-reproducing network, but otherwise you don't really need to look at the scale, yes? We just have these things connecting computers. And of course, I dropped out the 24. 24 is really useless. I don't have to pass to a limit because I don't have a limit to pass to. And so we can do this way. And of course, you can, I don't know if it's here or somewhere else. But of course, in a network, it makes sense not to look at this quantity, and so not to look at E over D divided by D to the third, but to go to E divided by D. That's what I'm trying to say. So because you have not a notion of scale, then this is perhaps the most natural thing to do, and it's very easy to compute. Okay? So, okay. So this is something which I already said. This invariance should be taken in tandem with other invariants for recognition problem. Okay, so now I have another, so we have the extent and we have the excess, which is a simple notion, and we made the connection between curvature, more specific Hantius, or if you want Menger, and excess. And there is another notion, which is a packing radius. So it tells you how dense you can pack balls. Okay? So this is a definition. And why should you pack balls? Why would I be interested from the viewpoint of the other courses in the school? If I want to do something like persistent homology, I might want to pack balls, no? Okay, so that's why you want to see how strong they are and how things appear and disappear. So this is it's a relation with the Czech and, for instance, complex and stuff like that. So again, there is another way of looking at this. Doing the Czech complex connects you to the homology and non-homology type through Ricci curvature, and that is a work again of Grove, but with Petersen. It's a classical work of, if you want, of sampling and coarse sampling of reconstruction of manifolds. But in any case, this is another metric invariant which goes from half of the diameter to 0. And so if we have this series of inequalities, and if you remember, for the extent we had a similar one. Yes, but they started above Somehow it goes different, but it's similar in spirit. Okay, so now that's all I wanted to say. I'm not trying to do theory, and I'm not trying to do the more deeper things of Groves and Petersen. That would deserve another talk and it's another ball game. But I'm trying to see how it works. Not entirely another ball game, but it's like American football in comparison to soccer. Okay, so let's try to see if these ideas work, yes? So these are a few networks. I forgot what the networks are. You'll see their names. So there are some small networks, some very small networks, some middle-sized networks, and some big networks which are smallish for anyone except me. So some of them are social, some of them are clearly biological in nature. I don't know, we'll see. These are the small and medium-sized ones, and these are bigger ones. So they're classical, so to say, available networks. You can download them from the internet, And they are good, A, because everybody knows about them, B, because since they are freely available, you can compare them, and three, because they come with all the information, spectral in eigenvalues, size, all Chigger constant, between us, whatever. Okay, so you can say a lot about it. Okay, and there is another type of network which I like very much, which is this one. It's a grid. So how do I obtain the grid? You just start with an image, which you can see the pixels. So if this is your grid, then these are the pixels of the image, and you have the neighborhood, the neighboring vertices, and you obtain the dual, it's a dual tessellation, but it's just a neighborhood. Graph this, I'm describing the neighborhoods. And this is what I obtain here. So this is an 11 by 11. Why 11 by 11? This is the largest small scale possible. If you take one pixel, it has no information. The eye is not able to understand. 3 by 3, 5 by 5 contain more information. The more information, the larger size you add, then the more means you take. So in the end, you lose information because you just obtain an average process. So you look for the largest possible meaningful neighborhood, which is 11 by 11. Why 11 by 11? There is a couple of papers of Mumford and one of his students who prove that this is optimal. I mean, there is a result that is the best geometrically and topologically, so to say. So it's a beautiful work, not well known enough. So this is the grid. You can see that there are interior points and boundary points, different colors. What people do usually, they discard the boundary ones because they have different degrees. So each point here has degree 4, obviously. But here you have degree 3, here you have degree 2. So why just peel them off? One trick, the other trick is to add another layer to copy the exterior one once more, and then that's what people do. So this is the original patch of an image, and this is the image. It's a dog. And I took that picture because it was a gray dog on a gray boardwalk with a gray background, and it's ideal. And please tell me which is the texture with this noise. It's for that, that's why I took the picture. Also, it was a very nice place to walk by. It was in Ischia. Anyhow, so that's how you do it, yes? So how you obtain that grid. Remember this? Remember so this is the stick model of an image. Each square is a pixel. You have a stick above, which means how luminous your pixel is, how white it is, or how dark it is. And then you connect the neighboring ones. And of course, you divide them to have triangles, perhaps. Okay. So why I showed you the picture of a dog, but when you want to prove people in imaging or in pattern recognition, then you can do something. You have to look at these classical test images, so textures. So there are two what is called stochastic textures, natural ones. There is something in between which is gravel here, and this is clearly artificial. Yes, they're just bricks. Okay, so we tested our invariance on this one. Okay, so if I'm going for the networks, so there was I have names. I forgot which goes to which, but they correspond to the pictures you saw. There's an enzymes one, an ecological one, some infections, transmissions, emails, chemical, and you can see there is little to no information. I can say much. I only can say that, that extent increases with Q and it's inverse proportional to the size of the network. The larger the network, the more density. And now we are passing to the other networks, which are larger somehow. And the same information can be said. And what you can say immediately that I didn't have a good programmer. For small networks, he went to Q3. Obviously, the next 3 is a 4. 3 bis is a 4. Sorry. So then comes a 5, yes? But here he didn't go for larger extent. So it shows a bit that, if you didn't guess it already, computationally, these things might be difficult. Yes, they're simple to define. Anyone can write the code, but making it run on something big, it's kind of problematic. But when so this is the extent. So it shows something, but when I go to the packing radius, I get basically nothing, yes? Everything is the same. It's almost constant or even quite constant. So there is very little information for networks content. Okay. Again, for the larger ones as well, nothing to say. Let's see about textures. This is excess. Okay, sorry, forgot about the excess. Not fair. I'm a big fan of the excess. So again, I don't know what to say about it, yes? Since I can't compare it to other networks of the same kind, it doesn't say much. But now I'm looking at these things for textures, and now I have all the invariants here, so you can see the 2 packing numbers and excess and the extents, which are much more interesting. You see there is variation at least, okay? So I can't say, by looking at this, can say that textures are more interesting. Okay, the other way around. These invariants are more interesting when you look at textures than at networks, at least the small networks. Why? Because they have more points, which are more densely packed. The distances are smaller. Yes, it's more realistic, more interesting metric spaces. So had I said only that, then I wouldn't have bothered you with this. But now I can look at the histograms. So if you remember, I had a grass. I can go back, but grass, forest, gravel, and bricks. And now I see the big difference. You see how these histograms are very similar? This is a bit of in between, but the histogram of excess for an artificial one is very different, but really very different. So opposed to what we know about curvature, if you remember for curvatures, I showed you yesterday? Only yesterday it happened? Okay, seems a long time ago. For you even more, I'm sure. So if you remember, I showed you that a natural network, so to say, made by natural processes that arise in natural processes, have this multiple hump distribution, yes? Structure. Here is quite the opposite. The bricks show you this double dash. distribution and y, because they do have two different themes. Sorry, I'll go back. So if you look here, you have one, the artificial one, which is very symmetrical, one type of big jump in curvature. Yes, when you jump from one to another, well, something like this. And then you have some internal noise. Oops, each brick is not of unique color. So that's what you see here. Okay, so this is about excess in textures. So when I go to the free extent, again, this is even more dramatic. Yes.
You guys did this way on which scale to photograph the texture in her comparison, because I would imagine that if you have the vertical lines of grass for really a both.
Oh, no. This is here. I have these standard images. So there are two ways of doing this. I look at 11 by 11 patches, always 11 by 11. I can do, of course, I can do an exploration or over all patches of all sizes. So either I choose a standard patch or I do an exhaustion of all the patches. But since these are more or less repetitive, it doesn't matter which patch you choose up to some.
Wouldn't the axis depend on how far away from the objects you are?
Which objects? I have this one here. This is my image. I take my knife and I cut an 11 by 11 thing. That's what I'm looking at. Okay, I don't get, or I didn't I understand.
How could you take the picture?
Yes, of course. So again, okay, now I understand your question is good. I don't take the pictures. I just analyze them. And that's what I said. You have to look at this stuff from the viewpoint. You have to sell it to the people who work in the field. Like with the networks, I have to convince people if I want to publish a paper in pattern recognition, I have to use these images. With the dog is another matter. But that's why I didn't do it for the dog, okay? Because I wanted to do it the way they want it. But okay, I understood the question. So you see here is super dramatic. The extent for images that are natural is just one jump. Whereas for bricks, you see how it's a very different one. So I don't know what so it's like this. You show me this picture, I can tell you this is man-made and this is natural. So it's a classification purely geometric, purely mathematical of textures just by looking at this is the power of histograms of symmetric. Yes.
So this process now the extent of a triangle?
Yes. Yes. And now if I am going to the pack 3, you see these are stochastic images, the grass and the trees. This is something in between, the gravel, which is almost repetitive, but not quite. And this is a repetitive one, and it looks very, very different. So why I was so happy and why this was, because it's good stuff, I think, because there is what I call the stochastic, natural stochastic textures, which were introduced some time ago and become popular again. And they say the following thing, okay, these things are made by some Brownian motion, I don't know. And this is captured by the image, this Brownian process, stochastic process, which resides behind the objects. And I'm curious if I can capture this. And I wasn't that convinced. And moreover, so then I tried. So when you look, it's me, guys. So how could I compare images forget about extents and stuff. What's the natural way of comparing networks? What did I show you yesterday? Curvatures, of course. So we tried this with curvatures, and we tried with this Olivier, with both flavors of Ricci, graph and triangles, with Menger curvature measure. That's why I needed the Menger curvature measure to talk about it. So you'll know, at least you know the name. And another measure which is the first measure introduced in geometric measuring graph theory. It goes back to Dufin, was Bott's advisor, and for electrical networks. So his notion is very geometric. You looked at the extremal lengths. How much time do I have? 5 minutes? 10. So there is, it's a notion not of curvature, but it measures the conformality, the departure of preserving shape. So conformal means that angles are preserved. Quasi-conformality means that they are almost preserved. So you want to see how far you are from preserving angles, means preserving the shape. Okay, so okay. This guy here and this guy here up to, you recognize them as being the same guy, yes? Why? Because when you navigate around the boundary, you see the same Mediterranean Sea, so to say, yes? Therefore, and so I preserve shape, I preserve angles, I preserve shape. I can modify shape a bit. So if I have this one and this one, they are not quite the same, but I recognize both of them as being sharks or tunas or whatever, yes, fishes. So it's a very natural way of looking. So in imaging, for instance, is very important, but the guys way before somebody was able of thinking about imaging, people are doing it for electrical networks. Because it comes, you have defined the row length in a graph, you have a positive function, and the row length is defined in this manner. So it's, and then you have a notion of area, which takes the weights. I'm going very fast, I know, but I'm trying to. You have an area. So the extremal length is the length which saw divided by the area, and you take a subpremum. What does it capture? It captures, and one of the extremal length is a modulus, and that's what people do in complex analysis. Why is it important? Because the extremal length is nothing but the effective resistance. If you have a metal plate, ferrometal plate, then the extremal length measures the resistance when going from boundary A to boundary 2. Yes. Well, I assume there is a function rho. It shouldn't be constant, yes? And of course, very serious people, and I mean, Finnish mathematicians do it in a, it's enough to do PhDs in the field, yes? But the original idea for extremal goes to Alfors in the 30s, I think, 40s, and Dufin look at this abstractization from the electrical networks point of view. And once you think of this as a plate, you think, okay, it's not a plate, I can think of a network. And instead of having a continuous plate of metal and continuous lines, I have a graph or a network, a communication network. So the first approach to the geometrization of networks and studying this geometry of network comes from electrical engineering and from a guy who did a lot of important things. And again, he did an important thing with Raoul Bott as an undergraduate, and they have an important theorem in electrical engineering. Before Bott went and became a great mathematician. Or he was already, I don't know. so this is a very natural notion from the viewpoint of somebody who comes from knows a bit of complex analysis and electrical engineering or wants to with extreme resistance metrics. And of course, I tried it. So again, we tried, I'm sorry, that would necessitate, to make it clear, a full talk, but I'm not volunteering. And I'm not volunteering you to listen to one. So we tried all these notions. Olivier, two Formans, and Menger measure, and a graph modulus. And it turns out that, okay, sorry, I should have said that the modulus is good because, again, it preserves quantitative information regarding the structure. It's small if G is thin. It's small on symmetric sets. Again, it detects symmetries. Think a bit, the longer this is, the higher the extremal length. If you have an eel, it has a lot of long extremal length. If you have flounder, then it's very symmetric, very round. So and it's a conformal invariant, as I said. So it's a good way of using it. So they give nice results, yes. Sorry? A thin? Well, I only can think of thin that having a long black backbone, let's say, and with some whiskers. This is the intuition. Where is thin? It's thin, but as a mathematician, I could define thin when it has a small extremal modulus, yes? So once I have a notion which captures this phenomenon, I define thinness for a graph using the modulus. Okay, makes sense. So that's how we do stuff. And mathematics. So we got nice results, except, and that's what I told you yesterday that I'll show you, except with Olivier curvature. I told you that Olivier curvature is a beautiful mathematical tool for imaging. It's kind of problematic. You get to some results, but there is no clear classificator. None of the curvature captures, not the measure, not the two Formans. So there are things that have the same distributions. Some are stochastic, some are not stochastic. That's what I'm saying. The growth Marvorsen is great because they really capture it. And it says something because in the end, images are just defined by very small distances, nothing more deep than that. But I said about Olivier. So this is an image, a text image. This time I only have it in grayscale. In any case, we compute only for grayscale. We start with a color image, we grayscalerize it, and then we compute. Because color would mean more dimensions. And so this is the image. So now this is, of course, so an image for me is just a grid, yes? So when I have a grid, I can compute Ricci curvature along an edge. So let's say along this edge. No, it's not a good edge color. Sorry. So I have two types of edges, left, okay. I have left, right, and right, up, down, yes? So you can compute the curvature of a pixel by taking into account all this and taking some mean. So here I am showing what happens only if you go left, right. So this is a Forman Ricci for left, right edges. And even if it's just left, right, so you lose a lot of orientation, you just go this way. You can still see the cracks in this. Yes. What do you see in Olivier? Nothing. Let's go now for the pixel one. So the pixel one would take at each, in the middle of it, each pixel would take its center. You would look at all the edges coming in and you would take their mean or their sum, whatever, yes? So this would be the scalar node curvature. So vertex, sorry. So here you see it, you recognize the image. What can you see in Olivier? zilch. Okay. So there is a big difference. So Olivier gives nothing. Not to say that computing this took some 30 minutes after it crashed the computer a few times. That's a small detail, yes. But since I didn't do the computing, it's easy for me to forget it. But I'm looking from the result point of view, okay? Because for these images, there is nothing about Brownian really transport and stuff. So just let me say that I would like to say that one would like to look at larger networks, a lot of variance, larger queues. I think that the real use would be to look at good, interesting images like, medical imaging, 3D, MRI or CT, to understand tumors, for instance, stuff like that. And of course, compare it somehow, which is more efficient. These simple methods with long computations, or perhaps persistent homology, or mixtures of both. That's it. And thank you. Of course, you all know this one, but this one you didn't see.